Grade 11, Unit 3, exercise. The first one. So, before I give the answers to the questions, I am sure you have already answered these questions. They are from your textbook. So, once you do that, you can compare your answers to make sure that you have written the correct answer. The first question. Explain the meaning of the following terms. First one, mixture. What is a mixture? Mixture is a substance which contains more than one components that do not combine chemically and can be separated by physical method. So here if I write the answer, mixture, matter consisting we can say two or more components that do not combine chemically and can be separated by physical methods. So that is a mixture. The second one is solvent. What is a solvent? A homogeneous mixture is known as a solution. In the solution, the component that is present in high amount is known as the solvent. There is only one solvent and more than one solutes present in a solution. So, solvent is the component present in highest quantity in a solution is the solvent. Then we have homogeneous mixtures. How do we classify mixtures as homogeneous and heterogeneous? Depending on the uniformity of the distribution of components. So, in a homogeneous mixture, the composition of the mixture is uniform throughout the mixture and all the properties are uniform throughout the mixture. So, here we can say mixture in which the composition is uniform throughout the mixture. That is known as a homogeneous mixture. And here students, to limit the writing, I haven't gone into saying this is a mixture, this is a solvent or this is a homogeneous mixture. I have only given the explanation. So, if you want to complete the explanation, you can say mixture in which the composition is uniform throughout the mixture is known as a homogeneous mixture. The same way, the component present in highest quantity in a solution is known as the solvent. And matter consisting two or more components that do not combine chemically and can be separated by physical methods are known as mixtures. I'll move on to the next question. A solute. So, as we discussed, in a homogeneous mixture or a solution, the components that are present in smaller quantities are known as solutes. Components present in small quantities in a solution are the solutes. And you know, in a solution there can be more than one solute. Solution. A homogeneous mixture is known as a solution. A homogeneous mixture. And we have solubility. This is something that you need to define. Solubility. The amount of solute that can dissolve in 100 grams of a solvent at a given temperature is defined as solubility. So, the maximum amount of solute that can dissolve in 100 grams of the solvent at a given temperature is defined as the solubility of a solute. I will move on to the next question. Write two properties of a homogeneous mixture or a solution. You all know what homogeneous mixtures are. The composition is uniform throughout the mixture, and also the physical properties such as transparency, color, density, all those are uniformly distributed throughout the mixture. So, those are two properties of a homogeneous mixture or a solution. So, here we can say the composition is uniform throughout the solution. And we can say physical properties such as color, transparency, and density are uniform throughout the solution. I will move on to the next question. Explain how a solvent can be polar or non-polar. When we take a solvent, we look at the compound of the solvent. When we say compound, the bonds that are present. If the bonds are polar covalent bonds and if the molecule is not symmetric, then that solvent becomes a polar solvent. But if it has non-polar covalent bonds or if the compound having polar covalent bonds is symmetric, then it will become a non-polar solvent. So, I will write that down here. So, a covalent compound that is not symmetric and has polar covalent bonds is a polar solvent. Examples, if we take water. You know this is a polar compound. Why? There are delta negative charges and delta positive charges. That is the partial charge separation. So, these are the polar covalent bonds and therefore, this is a polar covalent compound. So, this becomes a polar solvent. Similarly, if we take ammonia, that also has polarity. So, it is a polar covalent compound or a polar solvent. So, that is the first type. Then, if we take the non-polar substances, then we have a compound, a covalent compound that has only non-polar covalent bonds or has polar covalent bonds but is a symmetric molecule. Then it is a non-polar compound. So, two criteria satisfy the non-polar compounds. We'll look at some examples. So, if we take the example of, let's say, methane. Methane does not have any polar bonds. It has only non-polar covalent bonds. So here non-polar covalent bonds. Because all the CH bonds are non-polar covalent bonds. So therefore, this molecule is a non-polar compound. Whereas if we take carbon tetrachloride, now CCl bond is a polar bond, but this molecule is a symmetric molecule. Therefore, this is also a non-polar solvent. So here CCl is a polar bond, but the molecule is symmetric. Therefore, this is a non-polar solvent. So students, you have to remember, if there are only polar bonds, then and the molecule is not symmetric, then it becomes a polar solvent. If there are non-polar bonds, then no problem, that again is a non-polar solvent. But here you have polar bonds, but the molecule is symmetric. Therefore, it becomes a non-polar compound. With that, I will move on to the next question. Explain the following observations scientifically. Jack latex, that is Koehler, cannot be washed away with water. Why? Water is the solvent. It is a polar solvent. Inorganic polar solvent. What is Jack latex? It is a non-polar substance. So because of that, Jack latex doesn't dissolve in water. So that is what you have to write here. Water is polar. Jack latex is non-polar. Therefore, Jack latex doesn't dissolve in water. The next one, Styrofoam, regiform, can be dissolved in petrol. We will discuss the structure of regiform later. It is an organic non-polar compound. It is a polymer. Styrofoam is a polymer. It is an organic non-polar polymer. So petrol is again an organic non-polar solvent. So therefore, Styrofoam can dissolve in petrol. So here we can write both Styrofoam and petrol are organic non-polar. Therefore, Styrofoam dissolves in petrol. The last one, The moment the cap of a bottle of soda water is removed, gas bubbles evolve. We have seen this observation before. When the soda water bottle is closed, the carbon dioxide gas is dissolved in water because of the high pressure. You all know when pressure of gases increases, the solubility increases. And when we open the bottle, the pressure is released, therefore the solubility of carbon dioxide decreases. Therefore, you can see the evolving of gas bubbles. So, if we put this into writing, the moment the cap of a bottle of soda water is removed. So, here we have to say when the cap of a bottle of soda water is removed, the pressure inside the bottle decreases. Thus, solubility of CO2 gas decreases. Therefore, gas bubbles evolve. So, if you explain that, you give the answer for this question. I am sure you were able to explain all these observations. Now, we will move on to the next question. Stones mixed with rice are removed by sifting. This is a mechanical method. Which physical property of the components, rice and stones, is helpful in this separation? What is the physical property? When we put it into a container and try to separate it, the stones that are heavier or more denser remain at the bottom, whereas the lighter rice grains are separated when we do the sifting process. So, here it is the difference in density of particles that is used for separation. So, that is what you have to write here. Difference in density of particles. A very short answer. The next question, write a similarity and a difference between vaporization and distillation used to separate components in mixtures. So, you know what vaporization is? We allow the solvent to evaporate either by providing heat or allowing it to be exposed to the atmospheric heat. So, based on that, there is either evaporation or boiling. Then what happens? The solvent escapes into the gaseous state and the solid component crystallizes. That is the component that we need to separate out, the solid crystals. Whereas in distillation, what do? There are different types of distillation. There we provide heat. By providing heat, we convert the component that we need into the vapor form, collect it, condense it, and extract the required component. So, if we look at the similarity, in both vaporization and distillation, the components from the liquid, that is the solution or the liquid, has to go into the vapor phase. But the difference is that in vaporization, we evaporate the solvent or the unwanted components and get the wanted component in the solid form, whereas in distillation, the component that is needed is converted to the vapor form and condensed to separate it up. So now we can write the similarity and difference between vaporization and distillation. So first I'll write the similarity. So here in both methods, heat is supplied to convert components to their vapor state. That is the similarity. Then difference. What is the difference? In vaporization, the unwanted component, usually the solvent, is removed as vapor and the wanted component remains as solid. But in distillation, the wanted component is vaporized and condensed in order to extract it. So that is the main difference between the two processes, vaporization and distillation. I'll move on to the next question. Calculate the concentration of the solutions given in the following table. I'm sure you know how to calculate concentration. So here they have given the solute, the molar mass of the solute. What is a molar mass? The mass of 1 mole of the substance then the mass dissolved in the solution, amount of moles, the unit is mole, and the final volume of the solution. And here they want you to calculate the concentration of the solution, and that is in moles per decimeter cube. One example is done for you. The solute is sodium hydroxide, NaOH, and the molar mass is given to you 40. You all know how to calculate molar masses if you are given the relative atomic mass. Then the mass dissolved in the solution is 10, that is in grams. So how do we calculate the number of moles? Number of moles is mass over molar mass. That is what is given here. Mass is 10, molar mass is 40. So the number of moles is 0.25. And here we have the final volume. So that is to calculate the concentration. So for your convenience, just for you all to remember the equations, I will write the equation for moles. That is mass divided by molar mass. So grams divided by gram, mole minus 1. So you get the answer as moles. What is the equation for concentration? Concentration, we can write it in symbols. C equals N over V. Concentration equals number of moles of solute divided by the volume of solution. And N is in moles, we divide it by decimeter cube. Volume has to be in decimeter cube. If it was in centimeter cubes, what do we do? 1000 centimeter cubes equals 1 decimeter cube. So we have to divide the volume by 1000 in order to convert it to decimeter cube. So I will write that as well. 1000 centimeter cube equals 1 decimeter cube. So these are all what you already know. Just to summarize the information, I have written it here. Now we will get back to the calculation. So here we have the calculation concentration of the solution. Number of moles divided by volume. But since volume is in centimeter cubes, it has to be divided by 1000. When you rearrange the equation, it becomes into 1000. So 0.25 divided by 200 into 1000 is 1.25. Unit is given there, moles per decimeter cube. Then the next one, calcium chloride. Molar mass, calcium is 40 and chlorine has a relative atomic mass of 35.5. So if we add 40 plus 35.5 into 2, that will give us a value of 71 plus 40, it has to be 111 here. So molar mass of calcium chloride is 111. Mass dissolved 27.75 grams, and here they have given you the correct substituted value 27.75 divided by 111. That gives you a number of moles of 0.25. So the final volume of the solution is 500 centimeter cubes. We need to find the concentration of the solution in moles per decimeter cube. So what do we write here? 0.25 moles divided by the volume of the solution 500, and we multiply by 1000 by in order to convert it to decimeter cubes. Same as here. So if we calculate the values, 500 and 1000 get cancelled off. So 2, if you calculate the value, this will be equal to 0.5. So the concentration of the solution will be 0.5 moles per decimeter cube. Then we have the next solute, sodium carbonate, Na2CO3, and the molar mass is given to you 106 grams per mole. The mass dissolved is 53 and the amount of moles is 53 divided by 106, that's 0.5 moles, and the volume is 2 decimeter cube. We need to find the concentration. So moles 0.5 divided by volume. Volume is already in decimeter cubes. So what do? We do a direct substitution. Directly you can write the value as 2. So that will be equal to 0.25 moles per decimeter cube. Unlike in these two, we don't have to multiply by 1000 because the unit is already in decimeter cubes. The last one, hydrochloric acid, HCl. Molar mass is 36.5 and mass dissolved is also 36.5. So when you divide 36.5 by 36.5, the number of moles is 1. And the final volume is 0.5 decimeter cube. So to find the concentration, 1 mole divided by 0.5. So here again, we don't have to do a unit conversion. So 1 divided by 0.5 is 2 moles per decimeter cube. That is the concentration of hydrochloric acid solution. So I am sure students, you got all the values correctly. Now we will move on to the next question. What is the mass of magnesium chloride required to prepare 500 centimeter cube of a 0.5 mole per decimeter cube magnesium chloride solution? So it's easy when we read the question if we can write down the values. So the volume of the solution is 500 centimeter cube and the concentration is 0.5 moles per decimeter cube. What do we need to find? The mass of magnesium chloride that is needed to prepare this solution. So you have to start from the concentration and go back to the mass of the solute. So you know the equation for concentration. Concentration C equals N over V. You can remember students, either we can write it in words or we can use this equation with the symbols. So we know the concentration 0.5 moles per decimeter cube. That is equal to N is not known to us. That is what we need to calculate. And volume is 500. So if it is 500, we need to multiply it by 1000 in order to convert it to decimeter cube. So if we rearrange this equation, here we have 0.5 into 500 divided by 1000 moles will be equal to N. So then if I do the calculation here, we have 500 divided by 1000, so that's 2 divide 0.5, so you get 0.25. So 0.25 moles is equal to N. Is that what we need to find? No. We have to find the mass of magnesium chloride. To do that, we need to know the relative molecular mass or the relative molecular mass with the unit grams per mole, that is molar mass. So how can we calculate the molar mass? We know the formula of magnesium chloride, MgCl2. So for MgCl2, you have magnesium 24 plus chlorine 35.5 into 2, that will be 24 plus 71, that is going to be 95 grams per mole. That is the molar mass of magnesium chloride. Then we need to find the mass. What is number of moles? Equals mass over molar mass. So if we rearrange the equation, mass is equal to moles into molar mass. So what do we get here? We have the number of moles 0.25 into molar mass 95, and you will get the value in grams. So here if we calculate 0.25, I take it as quarter 1/4. So if I divide 95 by 4, then I get the value 23.75 grams. So that is the mass of magnesium chloride needed to prepare a solution of 0.5 moles per decimeter cube concentration, and the volume is 500 centimeter cubes. With that, I will move on to the next question. Select mixture or mixtures that the components can be separated by crystallization. As you know, students, when we say crystallization, the solvent has to be evaporated off and the solute has to precipitate or crystallize as solid. So, a mixture where the solute is a solid. If we look at the given examples, mixture of salt water. Yes, salt is a solid. So, we can crystallize the salt from salt water. So, this is one mixture that can be separated by crystallization. Mixture of ethanol. They are both ethanol and water. So, both are liquids. Then we can't use the crystallization process. Here we have mixture of acetic acid and water. Again, both are liquids. So, we cannot use crystallization. Mixture of copper sulfate and water. Yes, you all know copper sulfate is a solid. They are crystals. So, we can use this method of crystallization to separate copper sulfate from water. So, they have asked us to select the mixture or mixtures that components can be separated by crystallization. We have done that now. The next one, several salts are precipitated in the tanks during the production of salt. You know the process of production of salt. Arrange the precipitated salts, calcium carbonate, calcium sulfate, sodium chloride and magnesium chloride according to the descending order of solubility. So, what do you know, students? Initially, calcium carbonate precipitates when the concentration is 2 times more than seawater. Then calcium sulfate when the concentration is 4 times more than seawater. Sodium chloride when the concentration is 10 times more than seawater. And magnesium chloride precipitates while sodium chloride is precipitating but at a slightly higher concentration than 10 times that of the initial seawater. So there, calcium carbonate precipitates first because it has very less solubility. Then we get calcium sulfate, slightly more soluble in water. Sodium chloride is soluble in water and magnesium chloride is even more soluble in water. Here they have told us to arrange it in descending order, that is the decreasing order of solubility. So there we have to write the magnesium chloride first. Why? That has the highest solubility. So we will have magnesium chloride, that is more soluble. I can use the greater than mark. And then we have sodium chloride, then we have calcium sulfate and calcium carbonate. You can either write it this way, descending order, or we can just write it like this. Magnesium chloride, sodium calcium sulfate and calcium carbonate. So you can use this symbol or you can write it by writing comma, because you need to give the descending order of their solubility. I am sure that you got this order correctly. Now I will move on to the next one. What are the compound or compounds precipitated in manufacturing salt that dissolve in the atmospheric water vapor out of the following? Compounds with deliquescent quality. What is deliquescent? They dissolve in atmospheric vapor and become hydrated. They can liquefy. So that is the deliquescent quality. What is the compound or what are the compounds? Calcium carbonate? No, that precipitates in the first tank. Calcium sulfate precipitates in the second tank. Sodium chloride, that is the salt, that precipitates in the small tank. Magnesium chloride, that starts precipitating even before the precipitation of sodium chloride is complete. And that is the salt that has the deliquescent property. So here the compound is magnesium chloride, MgCl2. We'll move on to the next one. You are given a saturated solution of salt. What could you do to dissolve some more salt in that solution? You know, students, what saturated solutions are. A solution in which the maximum possible amount of solute is dissolved. So, if you add more solute, that will not dissolve in the solvent. It will remain as solid. If you want to dissolve that solid, what can you do? You can increase the temperature, because at higher temperatures, the solubility of a solid solute increases. Or in other words, we can say solubility of solid components increase with increase in temperature. So, if we heat the saturated solution, we can dissolve more solute. So, here the answer will be by heating the saturated solution, more salt can be dissolved. I'm sure you were able to answer this question. Next, I will move on to the 13th question. Iodine is not soluble in water. When they say not soluble, it means they are less soluble in water. Because you know we have iodine solution in the lab. We use it for the starch test and also we used it in the activity to demonstrate solvent extraction. Name 2 solvents that more iodine be dissolved. They are actually asking us to name 2 solvents in which iodine will dissolve more. So, as you already know, there are different solvents. Most of them are non-polar solvents in which iodine dissolves more. What are they? Hexane. We can name the solvents. Hexane, cyclohexane, acetone and carbon tetrachloride. So, we used carbon tetrachloride for the extraction of iodine from water. And we can also use these other solvents. Hexane, cyclohexane, acetone, any one of those can be used to extract iodine. I'll move on to the next one. Name 2 instances that solvent extraction is used. So, we use solvent extractions to increase the concentration of medicinal extracts and also to extract essential oils from plants. So, we can write any 2 examples. They have asked us to write name 2 instances that solvent extraction is used. So, here if I write the answers, or you can even say to extract iodine from an aqueous solution. So, that is also possible. Extraction of iodine from water. What else can we write? We can write extraction of essential oils from plants. Extraction of essential oils from plants. You can also write extraction of medicinal extracts and portions from plants. Any 2 of those examples. The next one. What are the qualities of existing and the second solvents when the mixture is separated from an existing solvent into another solvent? So, in solvent extraction, there are 2 solvents involved. What should be their qualities? The solvent should be immiscible. So, that is 1. Solvents should be immiscible. What is the second one? The solute should dissolve in the second solvent more than the existing solvent. So, the second one, solubility of the solute should be more in the, here they have said second solvent. Second solvent than the existing solvent. So those are the qualities that should be seen in the two solvents when we use them for solvent extraction. With that, I will move on to the next question. What physical qualities of the components are used when they are separated by using distillation? You all know what distillation process is. Any substance is provided with heat and it is converted to vapor form. Then the vapor is condensed. That is the basis for the three distillation processes. So there, how do we separate the components? Based on their boiling points, or we can say based on the difference between boiling points of components. So here I can write it as based on the difference between boiling points of components. So here I have given the full answer. They have asked what physical qualities of the components. So you can even just say boiling points of components. Next one, state one similarity and one difference between simple and fractional distillation. So again, both the distillation techniques. So we need to provide heat and bring them to their boiling point so that they get converted to vapor. So that is the similarity between the two processes. So if I write that down here, similarity components of the mixture are converted to the vapor form by providing heat. So that is the similarity. Then they have asked for a difference. What is the difference? If you take simple distillation, the example is simple distillation of well water. What happens there? Well water separates out, it vaporizes, then condenses. We collect the pure well water, whereas the impurities, the solid salts that were dissolved, remain in the distillation flask. So there we separate the impurities from the required compound. In fractional distillation, separation of different components from, say, petroleum crude oil. So there all the components are necessary for us, but we separate them based on the difference in their boiling points. So that is the difference between simple and fractional distillation. So here we can say difference. I will just underline the two. So in In simple distillation, the required component is separated from impurities. In fractional distillation, many required components are separated from each other. So that is the difference. Similarity, components of the mixture are converted to the vapor form by providing heat. If you want, you can also include, and thereafter they are condensed. The difference is, in simple distillation, the required component is separated from impurities, whereas in fractional distillation, many required components are separated from each other from the mixture. So that is the difference and similarity between simple and fractional distillations. I'll move on to the next question. When setting the Liebig condenser for distillation, it is fixed with a slant and the vapor is inserted through the top end of the condenser. The water is inserted from the bottom. What is the importance of inserting vapor from the top? Inserting water from the bottom. I have explained this to you all when we discussed condensers. What is the purpose of having it slant? So that there is an inclination. It's not either horizontal or vertical. So there will be an ease of flow of water as well as vapor, but in a slow manner. How do we make it slow and efficient cooling? Inserting vapor from the top. So you already know, usually vapor rises upwards. When we insert it from top, we are making it to move downwards. So what happens there? Vapor moves slowly and that helps in efficient cooling. At the same time, when we insert water from the bottom, what happens? Water fills up the full space and remains within the condenser while flowing through it. It completely fills the condenser. So therefore, vapor is coming down, water is moving upwards and they are in opposite direction and they remain in the condenser for a longer time. This will lead to efficient cooling. So that is what you have to write here. So the first one, when vapor is inserted from top, it moves down slowly and also gets cooler. Then Second one, inserting water from the bottom. Water fills the full volume of the condenser and flows through it continuously. So, when it flows continuously, both vapor and water are flowing in the opposite direction, giving rise to efficient cooling. I will write that as a common point. That is applicable to both these observations. So, when vapor and water flow in the opposite direction, we can say vapor condenses more efficiently. So that is the reason why we have it slantly and send vapor downwards and water upwards. With that, I will move on to the next question. Name some essential oils produced by vapor distillation in Sri Lanka. I am sure you know the answers and you have written the correct answer already. I'll write a few examples here. They have said name some essential oils. So we can write cinnamon oil, then lemongrass oil, clove oil, cardamom oil, even ginger oil, citronella oil, you can even think of eucalyptus and also black pepper. These are also different types of oils that are produced by vapor distillation in Sri Lanka. What is the technique you can use to find out the constituent colors of a colored toffee in the market? As you see the word color, you know what type of technique we have to use. Chromatography. Why chromo refers to colors. So, colored components can be easily separated and identified by chromatography technique. So, here they have asked for the technique. So, we have to write it as chromatography. So, with that students, I have come to the end of the questions in your textbook. I am sure you wrote the correct answers and you have confirmed your answers with my discussion. As practice, I will discuss some more extra questions with you all now. Extra question 1, select the correct answer. Factor that doesn't affect the solubility of solute is. You know the factors that affect the solubility of solid and liquid solutes as well as gaseous solutes. Nature of solvent. Yes. Nature of solute. That is where we talk about like dissolves like. Similar substances dissolve in similar solvents. Then temperature. When temperature of solid and liquid components increase, their solubility increases. But when it is a gas, the solubility of gases decreases with increase in temperature. So that also affects solubility. Atmospheric pressure. Does the atmospheric pressure affect any of the solubility? No. It is actually the pressure of the gases that affect the solubility of a gas in a liquid, not the atmospheric pressure. That is the pressure around us, the atmosphere. So this is not a factor that affects solubility. Separating salt from seawater is evaporation. Yes, because water evaporates off, the concentration increases and salt crystallizes. So that is a correct answer. Steam distillation, it depends on boiling points of components, separation of, let's say, essential oils from plant parts. Solvent extraction, yes, extracting one component into another solvent or extraction of essential oils. Then mechanical separation, there are many different types of mechanical separations like sifting, sieving, magnetic separation, but we don't use them to separate salt from seawater. So first one is the correct answer. Next question. Method used to extract cinnamon oil. This you know, it has to be what? Steam distillation. Vaporization doesn't occur here. Vaporization occurs either during the production of salt or sugar and examples like that. Fractional distillation, separation of petroleum crude oil. Steam distillation, yes, we use steam distillation for the extraction of cinnamon oil or essential oils. Then filtration, that is to separate the solid components from a liquid solvent or from a liquid mixture. So that is also not correct. Next one, answer that contains only the materials needed to prepare standard solutions in the laboratory. You all know how we prepare standard solutions in the laboratory. All the glasswares have to be very clean. We need a watch glass to weigh the solute, then a funnel and a wash bottle to transfer the solute completely into a volumetric flask where we dissolve the solute and make the correct volume of the solution. So those are the equipment or materials that are needed to prepare standard solutions in the laboratory. We'll check the answers. Volumetric flask, funnel, wash bottle and analytical balance to weigh the substance. That is correct. So the first answer is correct. In the second one, volumetric flask, wash bottle, yes. But we don't need a petri dish, we need a watch glass. Third one, watch glass, triple beam balance, yes. We can use any of the balance. Volumetric flask, we don't need a beaker. Then fourth one, funnel, again we don't need a beaker, but we need a watch glass and a chemical balance. So first answer is the answer that has only the materials needed to prepare standard solutions. So the next question. A method that is not used in day-to-day life to separate the components of a mixture. So as you already know, we use many of the physical separation methods to separate components of mixture in day-to-day life. We look at the answers. Sifting, yes, to separate particles from soil or separate particles from flour. We use the process of sifting. Then floating on water to separate dud seeds from the good seeds or rice from dud seeds. Then we use floating on water. We use sieving. Yes, again sieving, separating components, particles from flour. We use sieving. So we use the first three. Fractional distillation, that we don't use in our day-to-day life. It's either used in the laboratory or as an industrial process for separating petroleum crude oil, and there are many other applications. So fractional distillation, we also use fractional distillation to separate different gases from air. What is not an organic solvent? You know what organic solvents are. What are organic compounds? Compounds that are made up of carbon as a constituent element, or compounds that contain carbon as a main constituent element. So, you know many examples of organic compounds, and you know examples of organic solvents. Acetone, yes. Ethyl alcohol, yes. Water is an inorganic solvent. Kerosene is an organic solvent. So, answer is water. The next question. Extra question 2. Matter that contains two or more substances is referred to as mixtures. That is correct. What is the name given to the substances present in a mixture? What do we call them? They are called as components of a mixture. So here you can just write components or can say components of the mixture. Only the word components is also more than enough. Write the properties of a mixture. What are the properties of a mixture? The components are not chemically combined, and also they can be physically separated, or they can be separated by physical methods. So those are the properties of a mixture. If I write that down, components are not chemically combined. That is one property. Then the other one, components can be separated by physical methods. So those are two properties of a mixture. The next question. Extra question 3. What is the name given to the mixture with uniform composition? You know there are two types of mixtures. If the composition is uniform throughout the mixture, we call it the homogeneous mixture. So, a direct question, homogeneous mixture. Next one, what is the other main type of mixture and why? So, this is homogeneous. What is the other type? Heterogeneous. And why do we call it heterogeneous? Because the composition is not uniform throughout the mixture. So, if we write the answer, it is called the heterogeneous mixture. Why? Because the composition is not uniform throughout the mixture. So that is the reason why we call it heterogeneous mixtures. Next question. Extra question 4. Write 2 examples of solid-solid mixtures. There are so many examples. You all can write any relevant example. I will give 2 examples. One is, we'll say brass. All the alloys are made up of metals. They are a combination of metals. If we take brass, brass is a mixture of copper and zinc. So both are solids. So that is one example. So I will write brass here. Then what else can you write? We can say rice and sand. Both are solid components. Or we can even say copper and iron, just a mixture of copper powder and iron powder. Or even naphthalene and copper sulfate crystals. That is also a solid-solid mixture. So since we used naphthalene and copper sulfate for our activity, I will write that as an example. Naphthalene and copper sulfate mixture. So then we have the next question. Write 2 examples of solid-liquid mixtures. Normally you all know the solids dissolve in the liquid, and that is a very common mixture available to us. Most of the homogeneous mixtures, which are known as solutions, they are mostly solid-liquid mixtures. Not all, most of the examples that we use. Say sugar solution, salt solution, copper sulfate solution, sodium hydroxide solution, all these are solid liquid mixtures. So here I will write the answers as sugar dissolved in water, or you can say sugar solution. I wrote the first answer to show that sugar is the solid and water is the liquid. But if you write the answer as sugar solution, that is also correct. The same way we can say sodium hydroxide solution. Or you can say sodium hydroxide dissolved in water. So these are all different examples. I am sure you can write many more examples. I'll move on to the next one. Extra question 5. What are the main components of a solution? That you know very well. What are the 2 main components of a solution? There will be one solvent and more than one solute. So here if you write the answer as solute and solvent, That is correct. What is meant by aqueous solution? When we say sodium chloride aqueous, what do we mean? Sodium chloride is dissolved in water. Copper sulfate aqueous, copper sulfate dissolved in water. So, if a solid is dissolved in water, that is the solvent, then we call that as an aqueous solution. Or in other words, we can say in an aqueous solution, the solvent will be water, or mixture or solution in which water is the solvent, that is known as aqueous solution. So, here I will write the answer as solution in which water is the solvent. You can write the answer in your own words as long as it gives this correct meaning. I will move on to the next question. Write the name of a liquid gas mixture. You know a few examples for liquid gas mixtures. Oxygen or carbon dioxide dissolved in any water body, say seawater or water in the pond. That is an example of liquid gas mixture. Otherwise, if you take a closed bottle of soda water, carbon dioxide is dissolved in water. So, you can write any one of those examples. Write the name of a liquid gas mixture. So, I will write the answer as an unopened bottle of soda water. Why do we need to specify unopened bottle? Because then there is carbon dioxide dissolved in water at high pressure. And you know what happens when the bottle is open. The next one, what type of a mixture is an opened bottle of soda water? So, the next question, what happens when you open the bottle of soda water? The pressure is released, the solubility of carbon dioxide decreases. So, therefore, carbon dioxide gas is evolved from water, or it separates out from the mixture. So, here what type of a mixture is an open bottle of soda water? In an open bottle of soda water, you can see the carbon dioxide separately from water. So, the composition and physical properties are not uniform throughout the mixture. So, therefore, we call it a heterogeneous mixture. What type of a mixture? So, you have to say heterogeneous mixture. The next question. Extra question 7. Salt, that is sodium chloride, dissolves well in water. Why? Why? Because sodium chloride is an ionic compound, whereas water is a polar solvent. So, therefore, sodium chloride can dissolve well in water. So, here I will say salt is an ionic compound and water is an inorganic polar solvent. Here you can even complete your answer by saying, therefore, salt dissolves well in water. But this is the reason that is very important. Grease dissolves well in kerosene. Why? What is grease? It is an organic non-polar compound. And what is kerosene? Again, an organic non-polar solvent. So, their similar solute dissolves in the similar solvent, or like dissolves like. So, here you can say grease and kerosene are organic non-polar compounds. Therefore, grease dissolves well in kerosene. So that is how you explain these observations. Now the next question. Extra question 8. Write the ways of expressing the composition of a homogeneous solution. I am sure you can write all the answers correctly. There were many ways of expressing composition. So, what were they? First, we discussed the mass fraction. Then we discussed volume fraction. Then we had mass volume fraction. After that, what did we discuss? It doesn't have to be in the same order. We discussed mole fraction. And also, if you can remember, after these, we also discussed parts per million, ppm, and as well as percentages, mass percentage, volume percentage. I'm not going to include all those here. Then we discussed concentration. That was also an important method of expressing composition. So, the final one is concentration. If you like, you can also include parts per million as well as percentages. I'll move on to the next question. Extra question 9. What is the equation for the mass fraction of a solute? So, here if we consider the mixture as containing components A and B, then how do we write the mass fraction of the solute? Mass fraction of solute, let's say A, is equal to what? Mass of A divided by mass of A plus mass of B. This is the equation that you are used to. But here they ask for the mass fraction of a solute. So, or you can also write it as another method. So, here I will say mass fraction of solute is equal to mass of solute. So that is, instead of mass of A, we write it as mass of solute. And if a solute is present in a mixture, what is equal to mass of A plus mass of B? It is the mass of the mixture. So if they have said it is a solution, we can write mass of the solution. Since they have not mentioned that, we can use the term mixture. So here we can write it as mass of mixture. So both are correct equations. I'll move on to the next question. Extra question 10. 30 gram of magnesium sulfate is dissolved in 300 gram of an aqueous solution of magnesium sulfate. Find the mass fraction of magnesium sulfate in the solution. So when you see the term aqueous solution, you all know that it is the solute dissolved in water. So here there is 30 gram of magnesium sulfate in 300 grams of the solution, and we need to find the mass fraction. You have to write down the equation. Mass fraction of magnesium sulfate. So that is equal to mass of, I will write it as MgSO4 magnesium sulfate divided by mass of solution. So that is equal to 30 grams present in 300 grams. It's always better to substitute with the unit so that when it gets cancelled off, you know both the units are the same. In case you get one value in grams and one value in kilograms, then you know you have to do the unit conversion. So here gram and gram gets cancelled off. 0 and 0. So 3 by 30, that is equal to 1 over 10. You can leave it as a fraction like this, or we can write it as 0.1. With that, I will move on to the next question. Extra question 11. 200 centimeter cube of a solution was prepared by mixing 60 centimeter cube of ethyl alcohol with distilled water. Calculate the volume fraction of ethyl alcohol, volume fraction of water. So you know the equation to calculate volume fraction. So here I will write the equation first. We can directly write for ethyl alcohol. Volume fraction of ethyl alcohol is equal to what? Volume of ethyl alcohol divided by the volume of solution. So here they have given the volume of solution. Or else you can write volume of ethyl alcohol plus volume of distilled water. So here I will write it as volume of ethyl alcohol divided by the volume of solution. Students, it is always good to write the equation first, then show the substitution and finally do the calculation. And there are also, if you can substitute with the units, it would be even better, because when you get the final unit, it's easy for you to check whether your answer is correct. So here, if I do the substitution, volume of ethyl alcohol, what is the volume? 200 centimeter cube of the solution prepared by mixing 60 centimeter cube of ethyl alcohol. So that is going to be 60 centimeter cube. And what is the solution? That is 200 centimeter cube. Here they have given the volume of solution, so we can directly substitute it. 200 centimeter cube. So you know the units will get cancelled off. 0 and 0 cancels off. So this is equal to 6 over 20. That can be further simplified 3 over 10. You can even write the answer as 0.3, because 3 over 10 can be simplified. So that is the volume fraction of ethyl alcohol. We have to find the volume fraction of water. There are two ways in which we can find the volume fraction of water. What are those ways? One is, again write the equation like this and find the volume fraction. What is the other method? You can subtract the volume fraction of ethyl alcohol from 1. Why? Always the sum of volume fractions of all the components in a mixture is equal to 1. And here there is only ethyl alcohol and distilled water. So therefore, since I have done this full calculation for the first part, I will use the simple method for the second part. Volume fraction of water is equal to 1 minus volume fraction of alcohol. I am using the shortened form. You can completely write it as ethyl alcohol or just mention it as alcohol. So that is equal to 1 minus, we can use the fraction 3 over 10. So then it will be equal to 7 over 10, or we can write it as 1 minus 0.3, that will be equal to 0.7. Both are the same answers. If you like, you can also do it in the direct method. Use the equation to find the volume fraction. I will move on to the next question. 80 grams of sodium hydroxide is dissolved in 180 grams of water. Calculate the mole fractions of sodium hydroxide and water. So here, if we need to calculate the mole fractions, first we need the number of moles of both sodium hydroxide and water. So what I will do is, I will calculate the molar masses and the number of moles first. So for sodium hydroxide, what is sodium? 23, oxygen 16, hydrogen 1, so it is 40 grams per mole. If we calculate the number of moles, what is that? There are 80 grams of sodium here. You divide it by 40 grams per mole, and that will be equal to 80 divided by 40, 2 moles. Then if we find the number of moles of water, what is it? Water, H2O, hydrogen 1 into 2 plus 16, that is 18 grams per mole. So there we have 180 grams of water. So number of moles is equal to 180 grams divided by 18 gram per mole. That is equal to what? 180 divided by 18, 10 moles. So now we have calculated the moles of sodium hydroxide and water. Then what do? Write the equation for mole fraction. So I'll write one equation, mole fraction of say sodium hydroxide equals number of moles of NaOH divided by moles of NaOH plus moles of water. If we substitute that, 2 moles divided by 2 plus 10 moles. That is equal to 2 over 12. Why the mole and mole get cancelled off? 2 plus 10, 12. If you simplify that, you get the answer as 1 over 6. Then what can we do? We can again use the same equation. Here we can have number of moles of water divided by number of moles of sodium hydroxide plus number of moles of water. Or else, we know that the sum of mole fractions of all the components in a mixture is equal to 1. So here there are only 2 components. Then we can calculate the mole fraction of water by subtracting 1 over 6 from 1. So here if I do that calculation, mole fraction of water equals 1 minus 1 over 6, that is 6 minus 1 over 6, 5 over 6. So that is the mole fraction of water. I am sure you know to do all these calculations correctly. I'll move on to the next question. Extra question 13. Determine the mass percentage of carbon in carbon dioxide. This is somewhat different from what we have done before. Here they have given only one compound, carbon dioxide. All this time we discussed composition of mixtures. This is a compound. But in this compound, you know there is carbon and 2 oxygen atoms. What is the molar mass of carbon dioxide? That will be usually given to you, but here it's not given. I will give you all the values, but you already know carbon is 12 and oxygen is 16. So if we calculate the molar mass, so here molar mass is what? Carbon 12 plus oxygen 16, but there are 2 oxygens. So that is going to be 12 plus 32, that is equal to 44. If you take 44 grams of carbon dioxide, how many or what is the mass of carbon present? There is only one carbon and the atomic mass of carbon is 12. So there are 12 grams of carbon present in 44 grams of carbon dioxide. So we can write it as 12 grams of carbon is present in 44 grams of carbon dioxide. So therefore, to calculate the mass percentage of carbon that is equal to, if you take 44 grams of carbon dioxide, there will be 12 grams of carbon. Why do we call it percentage? Because we are calculating for 100. So therefore 100. So here, if I simplify this, 12 and 44, you will get it as 3/11. If we simplify by 4, yes, 3/11 into 100. Gram and gram gets cancelled off. So that is equal to 300 divided by 11. That will be equal to 2727%. So the mass percentage of carbon in carbon dioxide is 27.27%. With that, I will move on to the next question. Extra question 14. What is a standard solution? You know the answer. What is a standard solution? A solution where the accurate concentration is known to us. So here we have to say a solution of which accurate concentration is known. Second one, how would you prepare 250 centimeter cube of 1 mole per decimeter cube solution of sodium hydroxide? You know the way of doing this. First, what do we need to do? We need to calculate the amount of sodium hydroxide that is needed to prepare this solution. So, I will do that first. How would you prepare 250 centimeter cubes, 1 mole per decimeter cube solution? So, if we find the number of moles of NaOH first, how do we do that? Concentration equals to number of moles divided by volume. So, if you multiply the concentration by volume, you will get the number of moles. So, that is concentration into volume. That is equal to 1 mole per decimeter cube into 250. But do we leave it like that? No, we have to divide it by 1000. Why? We need to convert it to decimeter cubes. So here 1000. So this becomes decimeter cube. And that is equal to 250 divided by 1000, that's 1/4, 0.25. dm minus 3 and dm cube get cancelled off. You get the unit as moles. So we need to take 0.25 moles of sodium hydroxide. But how do we measure it? In the unit mass. So we have to find the mass equivalent to this. So then the next one, mass of sodium hydroxide, that is equal to 0.25 moles into what? We need to find the molar mass of sodium hydroxide. And normally in a question they will give you the relative atomic masses. Sodium is 23, oxygen 16 and hydrogen 1. So there, if I show you the calculation, 23 plus oxygen 16 and hydrogen 1, that will be equal to 40. So that is the molar mass of sodium hydroxide. So to find the mass of sodium hydroxide, we multiply the number of moles by molar mass 40 grams per mole. That will be equal to what? 0.25 into 40. We will need 10 grams of sodium hydroxide. So that is a round value. But if we are preparing standard solution, we have to measure or we have to weigh accurately 10 grams. So when we say accurately 10 grams, it would be ideal if we can weigh 10.00 grams of sodium hydroxide. So that is an accurate measurement of the mass. So here, just to show you all that, I will write it as 10.00 grams. So if we use an analytical balance, it will be very easy for us to weigh this value. Otherwise, we can use a triple beam or 4-beam balance that is available in the lab. So then, what do we do to prepare 250 centimeter cubes of the solution? Now we have calculated the mass. Then we have to measure the mass accurately, or you can say weigh 10 grams of sodium hydroxide accurately using any balance. Then what do we do? Transfer all that into a volumetric flask. What should be the volume? 250 centimeter cube volumetric flask using a funnel and a wash bottle. And we have to make sure we transfer all the solutes into the volumetric flask. Then what do? We fill water up to about 3/4 of the volume. Mix the volume completely so that all the solutes dissolve well in the solvent, that is distilled water. Then we make the volume up to the volume mark. So you will have exactly 250 centimeter cubes of the sodium hydroxide solution. So here, since they have asked how would you prepare 250 centimeter cube of 1 mole per decimeter cube, there should be a minus here, 1 mole per decimeter cube solution of sodium hydroxide. So now I will write down the steps. So we will say weigh 10 of sodium hydroxide accurately into a clean watch glass. The second point, transfer the sodium hydroxide into 250 centimeter cube volumetric flask using a funnel and wash bottle. What is the third step? Transfer all the solute and add distilled water up to 3/4 of the volume. Once all the solute is transferred into the flask, add distilled water to 3/4 of the volume. Then what do? Mix and dissolve the solute well, and finally what do? Make the volume to 250 centimeter cube by adding distilled water correctly. Make the volume of the solution to 250 centimeter cube by adding distilled water correctly up to the volume mark. How do you add correctly up to the volume mark? If the volume mark is like this, the meniscus should be this way. The lower point of the meniscus should be exactly on the line. So that is how you make exact volume of fixed or definite concentration of a solution. That is a standard solution. Do you keep it aside like that? No. What do you need to do? You have to label the solution. So the last step, label the solution. And you know what you have to include in the label. Name of the solute, name of the solvent, concentration, date prepared, and also the person who prepared the solution, and you can include the name of the solution as well. So all those information have to be there in the label. So when we say label the solution, that means you have to include all the information and paste the label onto the volumetric flask. With that, I will move on to the next question. Extra question 50. How do you remove the chaff from rice? You know how it is done? By winnowing, using a winnowing fan. So here we can write the process as by winnowing. Winnowing. And you know how that is done. What is the physical property related to separation method you specified in part 1 above? When we say winnowing, they use the winnowing fan. Chaff is less denser than rice, so the rice and chaff get separated. So what is the physical property? We can either write it as density or better to write it as difference in density. In density. What is the method used to remove gravel from sand? How do we remove gravel from sand? By sifting. So here you can write the method as sifting. What property of the components of the mixture is used for the separation method mentioned in part 3 above? So that is sifting. What happens there? The sand is smaller in size, so it goes through the pores of the sieve, whereas the gravel particles are larger, so they are retained in the sieve. So what is the property that is used there? The difference in size of particles. So here, if we write the answer, what property? So here I will write it as difference in size of particles. That is what we use for separation. The next question, extra question 16. Write the name of the method used to separate gold from impure gold. What is the method used? We use the technique of vaporization. React gold with mercury, it becomes gold amalgam, and when you vaporize mercury, you get the pure gold back. So here write the name of the method used to separate gold from impure gold. It has to be vaporization. Vaporization. Right. What is the physical property related to the above separation method? The physical property is that mercury can evaporate quickly, whereas gold doesn't evaporate. So there, what is the difference? Volatility of the components. So here we can say difference in volatility of components. Okay. So that is the property that is used to separate gold from impure gold. Now I will move on to the next question. Extra question 17. What is the method of separation used in extraction of salt from seawater? Is it evaporation or steam distillation? So you all know when water evaporates off, salt crystallizes. So what is the process here? Evaporation. So we have to write the answer as evaporation. Then the next one. How do they produce sugar from sugarcane juice? What is the process? It is crystallization. So here, how do they produce sugar from sugarcane juice? It is by crystallization. crystallization. So there sugar crystallizes and separates from the liquid mixture. With that, I will move on to the next question. Extra question 18. Name an industrial process that utilizes crystallization. There are different processes. You all know the two most common ones. One is the production of salt from seawater. The other one is production of sugar or separation of sugar from sugarcane juice. So here when we say industrial process, we can write any one of those two. I will write production of salt, production of salt from seawater. The next one. What is meant by recrystallization? So what is meant by recrystallization? We dissolve the mixture containing the pure substance and the impure components in a solvent at a higher temperature and again allow the solution to cool down so that only the pure crystals crystallize. So that process is known as recrystallization. By doing this, what do? We separate the pure crystals from the impurities. So when they ask you what is meant by recrystallization, you can say the method of obtaining pure crystals by dissolving the initial crystals in hot solvent, then filtering it, and allowing the crystals to form again on cooling. So that is the process of recrystallization. I will move on to the next question. Specify an instance where solvent extraction is used. You all know a few instances. To extract essential oil from plants, then we extracted iodine from water into carbon tetrachloride, and also to extract medicinal components and portions from again plant extracts. So you can write one instance where we use solvent extraction. I will use the instance extraction of medicinal components and portions from plants or plant parts. You can write any one of the instance. The next one, petroleum crude oil is a mixture of hydrocarbons that you know, and you know what hydrocarbons are. How do you separate the components like petrol, diesel and kerosene from the crude oil? What is the method used for separation? We use fractional distillation. So, if I write the answer as fractional distillation, that is correct. The next one, briefly explain the concept of the above separation method, that is fractional distillation. What is the concept behind fractional distillation? There are more than one components in the mixture where the boiling points are distinctly different. So then the mixture boils at different temperatures and the components relevant to those boiling points will vaporize and they can be condensed and collected separately. So that is how we carry out the fractional distillation process. So if you are to write the concept, we can say components of a mixture have distinctly different boiling points the mixture is made to boil at these different temperatures so that the components vaporize separately and can be collected by condensation. So that is the basic concept related to fractional distillation. With that, I will move on to the next question. Extra question 21. Take a small amount of water into a petri dish and hold a strip of blotting paper vertically with one end immersed in water. What can you observe? So we have done a similar activity. What is this similar to? The chromatography technique. We immerse a strip of paper in water and the water travels upwards along the paper. So what is the observation here? Water travels upwards along the strip of paper. So that will be the observation there. What can you observe if you take a small amount of ether, acetone or ethyl alcohol instead of water into a petri dish and hold a strip of blotting paper vertically with one end immersed in the solvent? What will you observe? A similar observation. The liquid will rise up along the paper. Actually, when it is rising up, you can see the paper becoming wet, but you don't see a water or liquid flow there. So, there you can say the solvent will rise up the paper, or to be more specific, blotting paper. Here, if they have said, yeah. So, we can say the liquid will rise up along the paper. Then the third one. Mention the stationary phase and mobile phase in the above activity. What is the stationary phase? The paper doesn't move. So, paper is the stationary phase. So, here we can say stationary phase paper. And what is the mobile phase? Mobile phase. In the first one, it's water. And in the second example, there are 3 solvents mentioned. So, it can be ether, then we have acetone, or it can be ethyl alcohol. So, all these are different solvents. With that, I will move on to the next question. Extra question 22. Write the factors that should be taken into consideration when setting up a salter. I am sure you all can remember, students, the factors that need to be considered. If we discuss the factors, the soil has to be a clay soil with minimum percolation, and it has to be a flat surface and also closer to the sea, and there should be minimum rainfall, the maximum amount of blowing, and it has to be a place where the temperature is relatively high. So, those are the factors that you need to write here. So, here write the factors that should be taken into consideration when setting up a salter. I will say flat soil, then clay soil, with minimum percolation, then we need to have it closer to the sea, minimum rainfall, windy, dry conditions. So that covers most of the factors that you need to consider. The next one, how many types of tanks are present in a Salton? What are they? How many types of tanks? There are 3. So we can write the answer as 3. And what are they? Large, shallow tank. Then we have the medium tank and the small tank. So those are the 3 types of tanks present. Then the next question. Extra question 23. Write the concentration of seawater in the following tanks and mention the compound that precipitates in them. So first we have the large tank. There the concentration is twice the initial concentration of seawater. And what precipitates there? Calcium carbonate. So here I can say twice that of sea water, and the compound that precipitates is calcium carbonate. Then in the medium tank, the concentration is 4 times more than seawater. 4 times more than seawater. And what precipitates in the second tank? Calcium sulfate. Then we have the small tanks. What is the concentration there? It's 10 times more than seawater. So here 10 times more than seawater. And what precipitates there? That is sodium chloride. That is the main compound. Even before sodium chloride precipitation is completed, magnesium chloride and magnesium sulfate gets precipitated. But here write the concentration of seawater in the following tanks and mention the compound that precipitates in them. So you can leave out magnesium chloride and magnesium sulfate because we have written the main components. What are the salts that precipitate along with sodium chloride even before the precipitation is complete? So, and here you know the answer. We just discussed it. Since magnesium chloride and magnesium sulfate are the answers for this question, it's okay, we don't write it above. So here the salts are magnesium chloride and magnesium sulfate. What is the name given to the solution that is left after the precipitation of the compounds you mentioned above? After all these are precipitated, what do we call the solution? It's known as mother solution or bittern. There are 2 names. You can write any one of the names. Here I will write both the names. It's either known as mother solution or bittern. With that, I will move on to the next question. Extra question 24. Write 3 essential oils produced in our country. I am sure you know the answers very well. There are many essential oils. we'll write 3 examples. I will write cinnamon oil, citronella oil, and clove oil. You can write any other example as well. The next question. Extra question 25. What is the mass of urea required to prepare a 1 decimeter cube solution of concentration 1 mole per decimeter cube? So, to calculate the mass, you should know the molecular formula of urea. We have discussed this in your lesson before. You know the molecular formula. It is CONH2 twice. So, first we need to find the number of moles. What is that? C equals N over V. So, from that N is equal to C into V. 1 mole per decimeter cube concentration and the volume is 1 decimeter cube. So, we need to prepare 1 mole. So, to calculate the mass, 1 mole into, what do we need to know? The relative molecular mass or the molar mass of urea. So, here it is CONH2 twice. If I calculate the molar mass, carbon 12, you will be given the relative atomic masses for calculation. Carbon 12, oxygen 16, we have nitrogen 14 into 2 and hydrogen 1 into 4. That will give us a value of 4 plus 28, that is 32, 42 and 48, 50, 60. So, here if I write the relative molecular mass, that is going to be 60, but we need to use the molar mass, 60 grams per mole. So, that will be equal to 60 grams. So, what is the mass of urea required to prepare a 1 decimeter cube solution of concentration 1 mole per decimeter cube? And the next question. Find the mass of urea required to prepare 500 centimeter cube solution of concentration 1 mole per decimeter cube. Here you can see, student. This is 1 mole per decimeter cube. This is also 1 mole per decimeter cube. We calculated the mass for 1 decimeter cube solution. Here the volume is 500 centimeter cubes of solution. Do you need to repeat the calculation again? No need, because the concentrations are the same solute. Only thing is the volume is half the volume. So, you can directly calculate the amount of urea. So, if you want, you can mention volume is half. Therefore, the mass of urea is equal to 60 grams divided by 2, that is 30 grams. So, that is the mass of urea that is needed to prepare a 500 centimeter cube solution of concentration 1 mole per dm cube. So, students, with these questions, I have come to the end of the discussion on extra questions as well as the end of discussion on Unit 3 of your grade 11 science textbook. I am sure you all were able to understand the basic concepts related to mixtures, components of mixtures, types of mixtures, then the composition related to mixtures, the separation methods that we can use, and their applications. So as I always say, studying once is not enough. Listen to the discussion carefully over and over again until you get the very good understanding about the lesson. Read your textbook, practice all these questions, and then do many other additional questions. By that way, you can become very competent to answer any questions related to this lesson.